Welcome back to the deep dive. We are taking the mountain of documentation on system architecture and really boiling it down into the core decisions, the ones that underpin the apps we use every single day.
Yeah, absolutely.
Today's mission is, well, it's a deep dive into complexity, designing a chat system.
And not just any chat system. We are modeling an architecture that needs to be robust, resilient, and definitely fast enough to handle massive scale.
Right.
Our specific target today is a system serving 50 million daily active users. That's the kind of engineering challenge that, defines platforms like WhatsApp or maybe Facebook Messenger.
Okay, 50 million DAU.
Yeah.
That immediately sets the stage. When you are asked to design a system of this magnitude, the first steps are always the most critical, setting the scope.
Absolutely critical, yeah.
You have to know precisely what you are building, because trying to build, say, a low-latency, real-time messaging platform while also optimizing for, enterprise document sharing, that just leads to a broken design.
Exactly. The initial requirements define the entire architectural blueprint. We have to prevent designing the wrong system from the get-go. So for our deep dive today, we've kind of nailed down the following requirements based on our source material.
Okay, let's lay them out. The scale is fixed. 50 million daily active users, DAU.
Got it. 50 million.
Feature-wise, we need robust one-on-one chat. That's a must. And we need small group chat, but crucially capped at a manageable maximum of 100 members.
Okay, small groups. That's an important constraint.
Yeah, and we're sticking to text-only images for this design, but we're allowing a pretty large payload up to 100,000 characters per message.
Wow, okay. So text only, but potentially long text. And what about access?
Right, we must account for ubiquitous access. That means seamless mobile app support, web app support, and the system has to permit a single user to be logged in on multiple devices simultaneously.
The multi-device login. Phone, tablet, laptop.
Exactly, and that synchronization requirement, well, that adds immediate complexity to the data layer, doesn't it?
Oh, absolutely. We'll definitely need to dig into that.
And perhaps the most demanding constraints are on delivery and persistence. Low latency delivery is non-negotiable. If I send it, it needs to arrive pretty much now.
Real time is key.
And the history must be stored forever.
Forever. Okay. That combination, immediate delivery and permanent high-volume storage.
Yeah.
That's really what distinguishes our scope here. We are solving for high-volume, personal, sort of asynchronous communication.
Right.
And this requires different trade-offs compared to, say, a specialized ultra-low latency voice chat system like Discord, or maybe an office application like Slack, which has totally different compliance and search requirements.
Makes sense. That focus on speed and persistence takes us right into the foundation of the system. Part 1, choosing the right communication protocol.
Yeah, this is fundamental. This is where we confront the nature of the internet itself. The clients, whether they're mobile or web, they don't talk directly to each other.
No direct P2P.
Right. They connect to the central chat service.
Okay, so let's start with the sender side. When a client sends a message, that is inherently a client-initiated request, right?
Correct.
So, standard HTTP protocol, especially if you use a keep alive header, is actually surprisingly efficient here.
It is, yeah. The client basically says, hey, server, I have a message for user B, and the server acknowledges it. By using Keep Alive, we avoid that repeated overhead of establishing new TCP connections for every single message.
Cuts down on handshakes.
Exactly. It makes those client-initiated requests quick and scalable. And in fact, many foundational chat applications, including early versions of Facebook Chat, they initially relied on HTTP just for the sending function.
Okay, sending seems manageable with HTTP, but the moment we move to the receiver side, well, that's where the architectural nightmare begins, right?
That's the classic problem.
HTTP is request response. The server can't just, tap the client on the shoulder and say, hey, you have mail. We need the server to push the message somehow.
And that forces us to simulate a server-initiated connection. This is really the core challenge of real-time web apps. And historically, we started with two pretty primitive techniques to solve this.
Okay, technique 1, polling. Sounds simple.
Simple, yes, but incredibly resource-intensive. The client just periodically asks the server, maybe every few seconds, do you have messages for me? Anything new?
Constant nagging.
Exactly. It's a constant stream of short-lived connections. And, for the majority of the time, the server's just replying, no. Imagine 50 million users, each checking every 5 seconds.
Oh, wow.
The server resources CPU cycles for connection handling, memory, threads. They're just utterly wasted processing negative answers. It's fundamentally inefficient, especially for users who aren't actively chatting.
Yeah, that sounds awful at scale. And that inefficiency led to technique two, long polling, which I gather addressed the chattiness issue, but maybe introduced its own world of pain.
It did. Long polling is definitely an optimization over regular polling. The client sends a request, but the server holds that connection open. It essentially stalls
Okay.
until either a message actually arrives for that client or until a predefined timeout threshold is reached, say, 60 seconds. Only then does the connection close.
And then what?
Immediately upon closing, whether it got a message or just timed out, the client sends a brand new long polling request, restarting the whole cycle.
Okay, so it's much less wasteful when the user is just sitting idle for minutes. But what are the specific architectural drawbacks? Why isn't this the perfect solution for 50 million users?
Well, there are a few big ones. The first, and probably the most complex, is the load balancing complexity.
Ah,
So standard HTTP servers, they're typically stateless. And load balancers often use simple algorithms like round-robin distribution.
right.
So if user A sends a message, that request might hit, say, server 1, but user B's long polling connection, that might be held open by server 10 on the other side of the load balancer.
So server 1 has absolutely no idea where user B actually is connected.
Precisely. Server 1 then has to figure out, usually through some complex coordination layer, which specific server is holding user B's open connection, and then forward the data internally.
It sounds like it requires sticky sessions or some kind of internal routing map.
Exactly. Which starts to compromise the fundamental statelessness we really want in these high-scale backend systems.
Hmm.
Maintaining that state about who is connected where becomes this huge distributed challenge.
Okay, that's a big one. What else?
Second, determining true client disconnection is tricky. If user B's connection just silently drops, maybe they lose Wi-Fi or their phone battery dies, the server is stuck holding that connection resource open until the long polling timeout finally hits.
Wasting resources and delaying knowing they're actually offline.
Right. And third, even with long polling, if messages are infrequent, those periodic connection renewals after the timeout still generate unnecessary network activity and add a bit of latency. It's better, but still not ideal.
So all this effort, all these complex workarounds just to simulate a two-way connection, it really points us toward the obvious purpose-built solution, doesn't it?
It really does.
WebSocket.
WebSocket, the definitive modern answer, you'd say.
I would. It completely removes the need for these client-side tricks like polling or long polling. The key thing is that it's bidirectional.
Meaning both the client and the server can push data whenever they need to asynchronously.
Exactly. And crucially, it is persistent. Once established, the connection stays open.
I always found the setup quite elegant. It starts as just a standard HTTP request, right? And then using a well-defined handshake process.
It gets upgraded, the connection transitions to the WebSocket protocol.
Yeah.
And from an operations standpoint, a huge plus is that it uses the same ports as standard web traffic port 80 or 443.
Which means it usually plays nice with firewalls.
Right. It easily traverses firewalls, eliminating another potential layer of deployment headache. Okay, so WebSocket clearly solves the receiver problem beautifully. But looking at the entire design now, holistically, why not just use WebSocket for everything? If it solves receiving, why keep HTTP around for sending?
That's a great point. And increasingly, that's the direction designs go. Using WebSocket for both sending and receiving simplifies the entire design architecture dramatically.
How so?
Well, you transition from managing, separate HTTP services for sending and then this complex long polling logic for receiving to having just a single, persistent, predictable layer for all your real-time communication.
One connection type handles it all.
Right. This greatly reduces the implementation complexity, the testing surface area, the management overhead.
Yeah.
Especially at the scale of 50 million users. That simplification becomes critical.
That efficiency is vital. Okay, so we've pinned down WebSocket as the communication foundation. Now we need the infrastructure to actually support 50 million concurrent, persistent connections. That brings us to part 2, high-level architecture and data layer decisions.
Yeah, a system this large absolutely must be broken down into specialized services. We can categorize them broadly into maybe 3 main groups.
Okay, starting with the easy ones, perhaps. The stateless services or API servers.
Well, right. These handle all the auxiliary functions, things like account registration, maybe profile updates, handling the initial login requests, because they don't maintain session-specific data related to the chat itself.
They don't care which chat server you're connected to later.
Exactly. They're easy to scale horizontally behind a simple load balancer. They're essentially disposable and flexible.
Makes sense. And the contrast then is the stateful services.
And this is where our core chat server lives. It is stateful because it has to maintain that persistent WebSocket connection. It needs to track the current status and location, essentially, of each connected client.
Okay.
For efficiency in message routing and just managing those connections, clients are generally designed to stick to one chat server unless that specific server fails.
Got it. And the third category?
The essential third-party integration. Predominantly, this means the push notification servers, or PN servers.
Absolutely necessary for getting notifications when the app isn't even open, right? When it's closed or running in the background.
Exactly. Guaranteed delivery often relies on leveraging Apple's or Google's push notification infrastructure.
Okay, stateless APIs, stateful chat servers, push notifications. How do these all coordinate? How does a client find the right chat server?
That requires an internal nervous system, if you will. Yeah. We need service discovery. Components like Zookeeper or maybe Console are commonly used here.
What's their job?
Their job is to monitor the health and the current load of every single server in the cluster, especially the stateful chat servers. So when a client tries to connect, service discovery ensures they get routed to the optimal chat server.
Optimal meaning?
Based on things like geographical location, you want a server close to the user current utilization. Is the server overloaded? And just basic server health. It prevents any single chat server from getting critically overloaded.
Okay, that coordination layer is crucial. Now let's pause for a scalability reality check. This always surprises me when I read about it. Technically, a single, modern, high-spec cloud server. It could theoretically handle a massive number of concurrent users, couldn't it?
It's theoretically possible, yeah. If you assume maybe around 10 kilobytes of memory needed to maintain the state for one WebSocket connection,
Okay.
you could potentially cram, say, 1 million concurrent users onto a single server with maybe just 10 gigabytes of memory dedicated to those connections. That seems achievable on modern hardware.
It sounds achievable, but I suspect there's a catch.
Oh, it's a conceptual trap. In a real production environment, a single server design is an immediate deal breaker. It's rejected out of hand.
Why the single point of failure is obvious, but what else?
Beyond the SBOF, think about maintenance. If that one massive server needs patching, or if a critical bug emerges, that requires a restart.
You knock 1 million users offline simultaneously.
Yeah, exactly. You have a massive outage. A multi-server design, distributed across different failure domains, maybe different geographical zones, is absolutely non-negotiable for resilience and basic robustness. The single server idea is fine for a conceptual starting point, but not for production.
Right, so distribute a workload, handle failures gracefully. That brings us squarely to the data layer. We have this requirement: store everything forever. For 50 million users constantly generating messages, how on earth do we approach storage for that?
We really have to bifurcate the data based on its access pattern and its structure. First, there's what we can call generic data.
Like user profile settings.
Exactly. User profiles, settings, maybe friend lists, potentially server routing information.
Yeah.
This stuff is highly structured, relational in nature often.
Right.
And it's usually best stored in robust, traditional relational databases, SQL databases.
Okay.
These systems offer strong transactional integrity, high reliability, and we can rely on standard techniques like replication and sharding for availability and scale.
But that's not the hard part, is it? The truly unique challenge is the chat history data. This volume just breaks the traditional mold.
It really does. You have to understand the patterns here.
Yeah.
First, the sheer volume is just staggering. Platforms like WhatsApp and Facebook Messenger, they process in the tens of billions of messages per day.
60 billion messages a day, according to our sources. It's almost an incomprehensible volume of writes.
It is. And crucially, the access pattern is heavily skewed. Users predominantly access only their recent chats.
Right, the last few days, maybe weeks.
Exactly. Everything older than that becomes the long tail of relatively cold data. Now, while the read-to-write ratio for a typical one-on-one chat might be close to 1.1 overall.
Because every sent message is usually read once.
Right. We still need to support random access features. Users expect to be able to search their history or maybe jump back months or years in a conversation.
And that combination, enormous write volume, most data being cold but needing potential random access, that's where traditional relational databases start to struggle, isn't it?
They struggle specifically with index management at that kind of petabyte scale. When the index required to find an arbitrary message ID potentially spans trillions of entries, even with aggressive sharding, random access performance can really degrade significantly.
Okay, so the index becomes the bottleneck.
Pretty much. And this is precisely why we pivot to key-value stores, or more broadly, NoSQL databases, for the chat history itself.
Okay, no SQL for the messages. What's the specific benefit there?
Key-value stores like Cassandra or HBase are fundamentally designed for low-latency retrieval and critically easy horizontal scalability via partitioning. They handle that cold, long-tail data far more gracefully.
How does partitioning help?
Well, by designing the data model correctly, for example, we can use the channelid, which is the unique ID for a specific chat thread, as the partition key.
Ah, so all messages for one chat live together.
Exactly. This co-locates all messages for that specific conversation onto a relatively small number of physical nodes in the cluster. This drastically reduces the search space and the index complexity compared to trying to manage a single monolithic relational index for everything. Facebook Messenger uses HBase, Discord uses Cassandra. These are common choices.
Got it. Partitioning by conversation is key. Now, let's talk about the single most important element of that data model, the message ID.
Absolutely crucial.
It obviously must be unique, but it also must guarantee time-based sortability. We need to know the order messages arrived in. And we can't just use a simple create at timestamp, right? Because two messages might be sent milliseconds apart, timestamps might collide or be unreliable across servers.
Exactly. Timestamps aren't reliable enough for strict ordering, and since we're likely using NoSQL, we typically can't rely on the built-in auto-increment functionality you get in relational systems like MySQL.
So what are the alternatives for generating these unique sortable IDs?
There are two main approaches. One is the global sequence generator, famously exemplified by Twitter's Snowflake algorithm.
Snowflake IDs, complex but globally unique and sortable?
Highly complex, yes, but they provide guaranteed chronological ordering across the entire system, globally. This is really useful if you absolutely need to know which of two totally unrelated messages, maybe sent in two different chats, on two completely different servers came first globally.
Okay.
The downside is, well, the complexity and the reliance on a potentially centralized or coordinated generation service, which can introduce latency and has its own scaling challenges.
Right, another system to manage. But you mentioned that for a chat application, often a simpler solution is sufficient, the local sequence generator.
Yes. Think about it. In a chat environment, do we really need global ordering across all chats? Usually, no. We only truly need strict chronological ordering within a single chat thread.
The message sequence in my chat with you doesn't affect the sequence in my chat with someone else.
Precisely. Therefore, generating an ID that is only guaranteed to be unique and incrementally sortable within that specific chat channel is often sufficient.
And presumably easier to implement.
Much easier. It requires less network latency, as the ID might be generated locally on the chat server handling the message, or perhaps by a nearby generator service dedicated to a subset of channels. It avoids the massive overhead and complexity of a global coordination service.
Okay, local sequence IDs within a channel. That sounds pragmatic. So let's map this onto our actual table structures in our NoSQL store for a one-on-one chat.
Where the conversation is implicitly defined by the pair of users, the primary key can simply be the message ID. It's unique within that implicit channel.
Simple enough, but for group chat.
For group chat, where partitioning is essential for scalability, we need to use a composite primary key. Typically, it would be channelid message ID.
Ah, okay. So the channelid comes first.
Yes, and critically, the channelid serves as the partition key. This tells the NoSQL database all data for this channelid should live together on the same set of nodes.
Got it. So all messages related to, say, group 5 will reside together physically, meaning when user A wants to fetch the history for group 5.
The query goes straight to the correct node partition, or small set of partitions, in our Cassandra or HBase cluster. Highly efficient retrieval.
Excellent. This foundational work on protocols and data really sets us up nicely. It brings us into part 3, the deep dive into operational flows. How do all these carefully designed pieces actually connect and work together when a user, opens the app or sends a message?
Right, let's trace the flow. It really starts with service discovery and practice. Remember that component, maybe Zookeeper or Console?
Yep, the coordinator.
It's often the client's first stop after they've successfully authenticated. Its job is to provide that critical piece of information. Which specific chat server should this client connect its WebSocket to?
Okay, walk us through that initial login flow then. Let's say I open the app.
Okay, you open the app. Your login request with your credentials first hits the main load balancer.
Right, the entry point.
The load balancer routes the request to one of the many stateless API servers. That API server handles the authentication, checks your username, password, or token.
Assuming I'm valid.
Once you're authenticated, that API server makes a call to the service discovery system, Zookeeper. Zookeeper looks at its current data server loads, maybe geographic proximity.
And picks the best chat server for me right now.
Exactly. It might say chat server 2 is lightly loaded and near this user. It returns the address of server 2 back to the API server, which then passes it to your client device.
And my client then connects directly.
Yes. Critically, your client bypasses the main load balancer now and establishes that persistent WebSocket connection directly to the recommended chat server 2. That server then becomes your designated home for real-time messaging, at least until you disconnect or it fails.
Okay, connected. Now let's trace the most crucial process, a one-on-one message flow. User A sends a message to user B. What happens?
Okay, 6 key steps here. Step 1. User A types their message and hits send. The message travels via their persistent WebSocket connection to their currently connected server. Let's call it server 1.
Got it. Server 1 receives the message.
Step 2. Server 1 must immediately obtain the unique sortable message ID. It requests this from the appropriate ID generator service, likely a local one scoped to this chat channel.
Stamps the message.
Right. This gives the message its canonical sequence identifier. Step 3, the destination. Now, server 1 doesn't try to send it directly to user B or user B's server yet. Instead, it routes the message to the message sync queue, specifically to user B's partition or inbox within that queue.
The message sync queue or MSQ, you mentioned this earlier. Why the queue? Why not go straight to delivery?
The queue is critical for decoupling, durability, and handling offline users or server failures. It acts as a highly durable, persistent inbox for the recipient, user B in this case. For high performance and guaranteed delivery, this is often implemented using something robust like Apache Kafka, or maybe specialized durable queues in a system like Redis. It holds the message safely until it's confirmed as delivered to the end user.
So it's a buffer that guarantees the message isn't lost if something goes wrong before delivery?
Precisely, which leads to step 4, persistence. Almost simultaneously with putting it in the queue, server 1 also ensures the message is stored permanently in the key value store, like Cassandra. Now, regardless of temporary failures, that message is safe and indexed for history lookup.
Okay. Queued and stored. Now for the actual delivery attempt. Step 5.
Step 5 is the online check. Server 1, or a related service triggered by the queue, checks the present servers. Is user B currently online and connected to a chat server?
2 possibilities here.
Right. If B is online, the system determines which server B is connected to, let's say, server 2. The message is then forwarded internally from the queue, or the service reading the queue, to server 2.
And if B is offline?
If B is offline, the system skips the forwarding step and instead triggers the push notification PN servers. A push notification is sent via Apple's or Google's service to user B's device, telling their mobile OS, hey, you have a new message waiting.
Got it. And assuming B was online, step 6 is the final mile.
Step 6. Server 2, having received the message intended for user B, delivers it down to user B's device via their active WebSocket connection, message delivered.
That seems pretty solid, assuming everything works perfectly. But let's talk failure. What happens if, say, user B is online, connected to server 2, the message gets forwarded to server 2, but then server 2 crashes right before it delivers the message down the WebSocket?
Excellent question. This is exactly where the durability of the message sync queue is indispensable.
Yep.
If server 2 crashes, user B's WebSocket connection obviously breaks. Now, server 2 was responsible for pulling that specific message out of user B's partition in the MSQ and acknowledging its delivery. Because server 2 crashed before confirming delivery.
The message is still sitting safely in the queue, undelivered, unacknowledged.
Exactly, it hasn't been lost. Meanwhile, user B's device detects the dropped WebSocket connection. Standard behavior is for the client to attempt to reconnect almost immediately.
Right. And when it reconnects, service discovery will step in again.
Correct. Service discovery sees server 2 is down or unresponsive and routes user B's reconnection attempt to a new healthy server. Let's call it server 3.
Okay, B connects to server 3, now what?
Server 3 establishes the new WebSocket connection. Then the client device initiates a recovery process. It tells server 3, hey, the last message I successfully received and processed was message ID, say 123. It sends its Kermax message ID.
Ah, that variable you mentioned.
Yes. Server 3 then uses this information to check user B's message sync queue. It starts pulling any messages from the queue with an ID greater than 123. It drains the queue from that point onwards, delivering the missed messages, including the one server 2 failed to deliver, down the new WebSocket.
So the MSQ acts as that guaranteed recovery buffer. It ensures eventual consistency even if servers fail. No message is lost.
Precisely. It enables the system to recover gracefully from these kinds of transient failures.
This connects perfectly to our requirement for multi-device login and synchronization. How do my phone and my laptop, potentially connected to two different chat servers, ensure they both see the same message history, especially after one has been offline?
The mechanism relies almost entirely on that key value store being the single source of truth for history, combined with that simple local counter on each device.
The Kermax message ID.
Exactly. Every active device, your phone, your laptop, your tablet, independently maintains its own Kermax message ID. This ID represents the unique identifier of the last message that specific device successfully received and processed.
So, if my phone gets message ID 100, its local counter updates to 100. If my laptop was offline for an hour and its counter is only at, say, 90.
The laptop knows it has missed messages with IDs 91 through 100.
Okay, so how does it catch up?
When the laptop reconnects, or periodically, or when the user brings the app to the foreground, it queries the key value store. It essentially asks, give me all messages where the recipient ID matches my user ID and the message ID is greater than 90.
And because the message IDs are guaranteed to be sortable within the channel.
The KV store can efficiently retrieve just those missing messages. The laptop processes them, updates its Kermax message to 100, and voila, synchronization achieved. Each device effectively heals its own history gaps by pulling from the central permanent store based on its last known position. It's surprisingly straightforward.
That is elegant. Okay, let's address the added complexity of group chat flow. We limited groups to 100 members. If user A sends a message to a small group of, say, 10 people, what's the architectural choice for handling that? It's not one-to-one anymore.
Right. For these defined small groups, the most common and often simplest approach is message fan-out on write, or essentially copying the message.
Copying, meaning
When user A sends the message to their connected chat server, that server retrieves the list of, say, 10 members in that group. It then iterates through those 10 recipients and places a distinct copy of that single message into each recipient's individual message sync queue.
Whoa! So one sent message results in 10 messages being stored in 10 different queues. That sounds potentially expensive, especially in terms of storage and write amplification.
It does seem that way initially, yes.
Yeah.
There's definitely a write amplification factor equal to the group size, but what's the immense architectural gain you get in return?
Simplicity somewhere else.
Exactly. Simplicity and homogeneity on the client side. By placing a copy in every individual's inbox queue, their MSQ, the client synchronization logic never needs to change.
Ah. The client code is identical for one-on-one and group chat.
Pretty much. Whether it's a direct message or a message from a group of 100, the client simply checks its own personalized inbox queue. It doesn't need complex group-specific polling logic. It doesn't need to track sequence numbers for dozens of different groups independently. It just processes messages arriving in its queue. This approach is highly robust and scalable for groups capped at a reasonable size, like 100 or maybe up to 500 members, as seen in systems like WeChat.
Okay, so the trade-off is more work storage on the server side during the fan-out in exchange for much simpler, unified client logic.
Precisely. But you immediately see the limitation, right?
Oh, yeah. I imagine this completely breaks down if we allowed groups of, say, 1 million members, like a public channel.
It becomes mathematically and economically infeasible very quickly. If one user sends one message, the server would have to generate and store 1 million copies of that message across potentially millions of queues. The storage cost and the write load would be astronomical.
So how do systems handle those massive broadcast channels?
For systems designed for those huge groups of public channels, the architecture must switch. Typically, they move to a read-oriented model. The message is stored only once in a central table or location specific to that large group channel.
And clients have to actively poll.
Yes, clients interested in that channel must actively poll or subscribe to that specific channel's storage location directly, rather than relying on personalized inbox queues, SQs, for delivery. It's a fundamentally different model. But within our defined scope of max 100 users per group, message copying is often the winning trade-off for delivery speed and synchronization simplicity.
Got it. Scope dictates the architecture again. Okay. Moving beyond the message content itself, we need to cover that other key feature, knowing if someone is available. Part 4, managing online presence.
Right, the little green dot. The presence servers are dedicated services specifically for this task. They manage and broadcast user online status information, again, typically utilizing those persistent WebSocket connections for real-time updates.
And where is the status actually stored?
The authoritative status is stored and constantly updated in the key value store, just like message history perhaps, or maybe a dedicated cache like Redis. We track the user's current online status, online, offline, and importantly, their precise last activate timestamp.
Okay. Explicit status changes seem easy enough. User logs in, update the KV store status to online, and timestamp now. User explicitly logs out, update status to offline.
Correct. Those are the straightforward cases.
But the real-world complexity comes from intermittent connectivity, right? Like, I walk into a subway tunnel, my phone loses signal for 10 seconds, then reconnects when I come out. We don't want my presence indicator frantically flipping from green to gray and back to green for that short blip. It's annoying for my friends.
Exactly. That intermittent connection problem, or just general network flakiness, would create a terrible user experience if the status updated instantly on every detected connection drop. The solution is the heartbeat mechanism.
Okay, how does the heartbeat work?
The user's client device phone, web app, periodically sends a very small, lightweight packet, the heartbeat, to its connected presence server, maybe every 5 seconds or so.
Just a little, I'm still here?
Exactly. And the presence server on its side uses a timer associated with that connection. It only considers the user truly online if it has received a heartbeat from them within a defined threshold window, say the last 30 seconds.
Ah, so there's a grace period.
Right. If the client stops sending heartbeats, perhaps because the connection silently dropped in that tunnel, the presence server doesn't immediately mark them offline. It waits. Only if it fails to receive a heartbeat within that 30-second window does it finally update the user's status in the KV store to offline.
I see. So the technical choice here directly links to improving the user experience. We accept a slight delay, potentially up to 30 seconds, in marking an abruptly disconnected user as offline.
In order to prevent that highly annoying UX, the presence light constantly flashing just because they walk through a patchy Wi-Fi area or their phone briefly switched networks. It prioritizes perceived stability over absolute instantaneous accuracy of the offline status.
Makes sense. Okay, so the presence server determines the status using heartbeats. Now, how do the user's friends get notified of that status change? Let's say I just came online. How does user B know? This requires the online status fan-out.
Yeah, we need to propagate that status change efficiently. This is where the publish-subscribe, or pub-sub, model comes in very handy.
Okay, pub-sub for presence. How's it set up?
The presence servers effectively maintain a pub-sub infrastructure. Conceptually, you can think of it as having a specific channel for each relevant relationship. When user A comes online, their presence server publishes a status change to online event to all the relevant channels, maybe channel AB, channel AC, channel ED, for each of A's friends.
And user B, C, and D are already subscribed to those respective channels.
Exactly. Their clients, through their own connections to presence servers, are subscribed to listen for events on channels related to their friends. So when that A is online, event is published.
It gets instantly pushed out via WebSocket to all connected subscribers B, C, and D.
Right. Ensuring those near real-time status updates you see in your friend lists or chat headers.
Okay, that sounds highly efficient if I have, a few hundred friends.
Yeah.
But again, let's push the scale boundary. What if I'm in one of those large community servers or group chats with, say, 50,000 members? And their online statuses are constantly changing as people connect and disconnect. Is this pub-sub fan-out strategy still sustainable?
No, it typically isn't. It introduces what's sometimes called an exponential fan-out problem, or a thundering herd problem for status updates. If one popular user coming online generates 50,000 downstream notification events that need to be processed and sent,
The system would just choke on presence updates.
it can quickly choke, yeah. The load on the presence servers and the network traffic for just status updates becomes excessive. This forces a key scalability optimization for very large communities or channels.
Which is?
We often abandon the real-time pub-sub status updates entirely for members of those very large groups. Instead, the online status for users in that massive channel is fetched only on demand. Meaning the client only asks for the current status of users in that large group when the user actually enters that specific chat room or channel view, or perhaps when they explicitly hit a refresh members list button.
So it's lazy loading for presence in big groups.
Exactly.
Yeah.
It's a pragmatic scaling choice. It prioritizes overall system performance and stability over maintaining absolute real-time presence accuracy for potentially tens of thousands of peripheral users whose status isn't critical at that exact moment. You trade real-time for scalability.
That structural differentiation based on scale and the perceived importance of the data, that really feels like the hallmark of good system design at this level.
Okay, wow. We have covered a lot of ground. The fundamental communication protocols, the high-level architecture, the critical data layer decisions, and these detailed operational flows for messaging and presence.
We have. And it's worth remembering before we wrap up that we focused almost purely on the mechanics of text messaging. Real world chat systems obviously need significant additional engineering just for handling media.
Oh, absolutely. Photos, videos, voice notes. If we were to continue this design exercise, the next module would absolutely have to delve into handling large media files
Right, which means thinking about offloading those files to a distributed cloud storage system like Amazon S3 or Google Cloud Storage.
and managing all the related features like automatic compression, maybe transcoding videos for different devices, generating thumbnails efficiently.
Exactly. All while ensuring the chat message itself only contains a lightweight pointer or identifier for that stored media object, not the whole binary blob. And we also only briefly touched on load time and optimization. For a truly globally scaled system like this, reducing latency involves more than just picking the right server. It often involves edge caching strategies.
Definitely. You mentioned Slack earlier. Think about how systems like their flannel architecture work to maintain caches of metadata, recent history, and user information closer to the user geographically.
Right, so accessing your recent chats feels instantaneous because a lot of it might be served from an edge location near you without having to traverse the entire network back to the central data center every single time.
It's another layer of performance optimization crucial at scale.
Okay, that provides great context for the scope of the remaining challenges. So let's quickly recap the core architecture we did build today. We rely on that persistent bidirectional WebSocket connection as the foundation for real-time.
Yep.
We utilize stateless API servers for auxiliary tasks like login and profiles, and stateful chat servers, coordinated by service discovery like Zookeeper, to handle the actual real-time message traffic and connections. We ensure eventual consistency, durability, and handle offline delivery using those durable message sync queues, maybe Kafka acting as per-user inboxes. And all chat history is stored permanently and accessibly in partitioned key-value stores like Cassandra or HBase, plus dedicated present servers using PubSub and Heartbeats for status.
It's a robust system designed for that immediate, reliable text delivery and permanent storage we aimed for. But it's important to note the entire design we've discussed rests on one core assumption,
Which is?
that the chat service providers or infrastructure, our servers, can actually read the data it is storing and forwarding. We need to access message content for things like generating push notification previews, potentially indexing for search, maybe content moderation.
Right. Our design assumes server-side access to the plain text messages. Which brings us perfectly to our final provocative thought for you, the listener, to ponder.
Okay.
We designed this entire system assuming the server could manage and access the message content. But many popular systems like WhatsApp famously employ end-to-end encryption or E2E.
Right, where only the sender and the intended recipients hold the cryptographic keys required to decrypt and read the message content. The server itself only ever processes encrypted ciphertext.
So here's the challenge. If the server receives an encrypted message from user A, generates a message ID, persists that encrypted blob to the key values store, but the KV store now contains data that the server itself cannot decrypt. What technical challenges does E2E encryption introduce to the architecture we just spent all this time designing?
Think specifically about the consequences for maybe two critical functions we discussed. First, message synchronization across multiple devices belonging to the same user. If my laptop hasn't seen a message yet, and that message sits fully encrypted in the KV store, how does my laptop get both the encrypted ciphertext and the necessary decryption key to read it, especially if the key distribution also needs to happen without the server seeing the key? How does multi-device sync work securely?
That's a big one.
And second, think about user-facing features. If we wanted to implement a search function, allowing users to search their own message history by keyword, how can we possibly build a search index on the server side if the server cannot read the text content of the messages it's storing? Does search have to move entirely to the client device?
Oof. Yeah, E2E encryption seems like it would fundamentally break or force a major redesign of several parts of the system we laid out.
It introduces a whole new layer of complexity, particularly around key management, device synchronization, and server-side functionalities that rely on content access. That's definitely the next level of challenge in secure chat system design.
An essential problem to ponder as privacy and security become ever more critical. Well, thank you so much for guiding us through this incredibly detailed and really expansive deep dive today. It was
My
fascinating.
pleasure. It really highlights how system design at this scale requires constantly balancing robustness, scalability, cost, and efficiency at every single decision point.
Absolutely. If you enjoyed this analysis and want more deep dives into complex engineering challenges like this one, be sure to follow the show wherever you get your podcasts. We'll see you next time on The Deep Dive.